Okay, so now let's write down what this energy actually is. So we've got the unperturbed energy, and now I'm going to use a formula from first order perturbation theory. And let me write down the term coming from second order perturbation theory. There's a sum over m here, which means it's a complete sum of all possible states that could contribute. Okay, so okay, good. So first of all, let's talk about why we had to go to second order. So the second order term is sitting over here. Okay, so that term that I just underlined in green. Okay, so we start off, and En naught is just the unperturbed energy. Then we've got the first correction. The first correction tells us that we start off in state M, we start off in state N, we then interact with the perturbation H1, and we return to state N. Let's imagine that N is a single particle state. Okay, so I'm always going to imagine that N is a single particle state. I could be studying, say, a single particle. That's all I'm saying. And I'm calculating the energy of the single particle. Now look at the second order term, the term underlined in green. So I start off with the state N, which is a single particle state. I then interact and I make a transition to the state M. Then when I'm in the state M, I make a transition again by interacting back into the state N. So I jump from N into M, and then from M back into N. And each transition is because of an interaction with H1. The state M that I transition to could be any state in the theory, and in particular, it could be a multiparticle state. So the reason why we had to go to second order is that the second order term includes the first multi-particle corrections. They're inside this term sitting over here. And we want to estimate how big those multiparticle corrections are, so we had to go to second order. So we want to estimate how big the multiparticle terms are compared to the single particle terms. So to do that, I want to estimate how big the various terms are. So to start off, let's look at this term, which is first order in G. How do we estimate how big that is? Well, I'm going to imagine that I'm working in a box, okay? If I'm working on a box, I can certainly normalize my states. So these are normalized to delta Nm. And what you can see is delta Nm, this is just the Kronecker delta. So it's either 1 or 0. So the right-hand side of this equation is certainly dimensionless. That tells me that both the ket and the bra are dimensionless. Okay, so the bra and the ket are both dimensionless. What about G? Well, G, the coupling, I also know is dimensionless. You see, look at this formula that we had here. H is an energy, H naught is an energy, and H1 is an energy. So we have energy equals energy plus G times energy. So G has to be dimensionless. So this term underlined in blue is the coupling, which is dimensionless, the bra, which is dimensionless, H1, which is an energy, and the ket, which is dimensionless. So this term itself has the dimensions of an energy. Now, what energy is that? Well, that's the energy of interaction. So think about a particle that I throw up into the air. So I throw the particle up into the air and it returns down to Earth. It is always accelerating. Why? Because it's interacting gravitationally. And what I might ask is, what is its gravitational potential energy? So what is the value of mgh? Well, certainly you know how to calculate the value of mgh at this highest point. What you would do is you would take the velocity with which I launched this particle, or it could be anything, a ball. So let's take the velocity with which we launched the ball. We would calculate its kinetic energy. Its kinetic energy is a half mv squared, and we would set this equal to mgh. So the energy of interaction, the gravitational potential energy, is set in this problem by a half mv squared. So when I want to estimate the size of this underlined term, well, the size of it, it'll be approximately mv squared. Now, you'll notice that I dropped the 1/2. Why did I drop the 1/2? Well, I don't know if it's going to be exactly mv squared. Maybe it'll be 1/10 of mv squared. Maybe it'll be 1/4 of mv squared. But the important point is the size of this term is set by mv squared. Good. Now let's take a look at the multiparticle terms. What you can see is I've got a factor sitting over here and a factor sitting over here, okay? Each of these factors are going to be of size mv squared. The argument is just what we gave for the first order in perturbation theory term. So we've got an mv squared times an mv squared. What we now have to ask ourselves is, how large is the denominator? So this En0 minus Em0. Okay, so we're working in a regime where the velocity is small enough that the relativistic corrections are small. They're not zero, but they are small. And in this situation, previously we had expanded the energy. And the answer that we got, let me just put back the mc squared here because that'll be important. The energy of the state was mc squared plus a half mv squared plus this relativistic correction. Now, when we think about these terms, we know that V over C is very much less than 1. So we know that we can really write the energy of a single particle state as mc squared plus something small. The state n is a single particle state, so we know that En0 will be equal to mc squared plus something that is small. So we don't have to worry about the small stuff. The size of En0 is set by mc squared. Now, to get a genuine multiparticle correction, we have to consider a state n that is a multiparticle state. So imagine that M is a 4-particle state. In this case, the biggest contribution to the state's energy is again coming from the mass. So Em0 is something like 4mc squared, and then there will be much smaller corrections because of the kinetic energies of the particles and interactions and so on. So again, plus small. And that means that if I work out what is En0 minus Em0, well, this difference really is dominated by the energy stored in the masses of the particles. So for this case, we'd get 3mc squared plus some small corrections. But again, we're just interested in the size of this term. So we would say the size of this term is set by mc squared. And it's because it is being set by the difference in the mass energy of the particles. Okay, so this last term in the denominator is like mc squared. Okay, so I want to summarize these sizes for our term En. So when we look at En took the form of mv squared. This was all the single particle terms. And then the multi-particle corrections looked like mv squared times mv squared over mc squared. And you can see that this looks like mv squared plus mv squared. And now the m's cancel, and we get a v over c squared. And then, of course, there would be other terms correcting this. But what you can see very clearly, so this is the multi-particle correction. And now I want to write down a conclusion. Let me remind you, we said that kinematical corrections are of size v squared over c squared. But what you can see, I mean, look at this equation. This is where we drew our conclusion from. If we look at the equation that we've got here, we can clearly conclude that multi-particle corrections are of size v squared over c squared. And this is exactly the same size as kinematical corrections. And this is exactly the result that we wanted to show. So the conclusion is that multi-particle corrections are of exactly the same size as kinematical corrections.